In the boundless tapestry of the cosmos, where the relentless march of entropy weaves through the vast expanse of the universe, lie mysteries that defy our deepest understanding. Black holes, those enigmatic behemoths, warp space-time, challenging the very fabric of our physical laws, while dark matter, invisible yet fundamental, silently orchestrates the cosmic dance of galaxies. This journey through the cosmos is an odyssey into the unknown, where the unraveling of entropy, the immensity of the universe, the mysteries of black holes, and the elusive nature of dark matter converge in a symphony of celestial wonder, inviting us to explore the infinite complexities of our universe. In the infinite depths of the universe lies a fundamental principle, as mysterious as it is omnipresent. This force governs the very fabric of existence, yet remains elusive to the casual observer. This is the story of entropy, a concept that reveals the hidden order in the apparent chaos of the cosmos. Here on Earth, entropy is evident in every rustling leaf, every rolling wave, and every moving cloud. It's the quiet organizer of natural processes, from the simplest to the most complex. But what is entropy really? It's a phenomenon often misunderstood as an ordinary disorder, but it's more than that. Entropy is a transformation, a movement from order to disorder, from concentration to dissipation. This is exactly why your coffee gets cold, why the ice melts, why the scent of flowers dissipates in the air. So let us understand how an order is hidden in what appears to be chaos, and how does this mysterious force shape our entire environment, from the smallest particle to the largest galaxy, and even the very course of life itself. There is a hidden force at work in every corner of our world, from the quiet forests to the bustling hearts of our cities. This force, often unnoticed, plays a key role in the great work of the universe. Imagine a dewdrop on a leaf, shimmering in the morning sunlight. As the sun rises, the dewdrop slowly disappears, and its particles disperse into the air. This phenomenon illustrates a fundamental principle of nature, the transition from a concentrated state, the dewdrop, to a dispersed state, the water vapor in the air. At the molecular level, this principle manifests itself as the tendency of particles to move from a state of concentration to a state of dispersion. This is similar to the way a crowd disperses after a concert, moving from a structured gathering to random scattered groups. In the center of our cities, this principle is reflected in the rhythm of daily life. The concentrated bustle of the morning rush hour gradually fades away as the day progresses. Entropy is often misunderstood as simple chaos or disorder, but it's much more nuanced than that. It's about transformation and change. Like a sandcastle slowly crumbling under the merciless waves, entropy is the inevitable transition from order to disorder. This concept is encapsulated in the second law of thermodynamics, a fundamental principle of physics. It states that in any closed system, entropy will either remain constant or increase over time. In other words, the natural course of the universe is toward greater dispersion and disorder. From the grand scale of the cosmos, where stars and galaxies form and disappear, to the minutiae of our daily lives. This principle is a universal constant. It governs the birth and death of stars, the flow of rivers, and even the fading heat in a coffee cup. Imagine a steaming cup of coffee left on a table. Over time, its heat dissipates into the surrounding air, cooling the coffee. This is entropy in action, redistributing energy from a concentrated state, hot coffee, to a more diffuse state, a cold room. Or take an ice cube melting on a warm day. the structured, solid form of ice turns into a puddle of water, whose molecules are free to move. This transition from a solid, ordered state to a fluid, disordered state is a classic example of increasing entropy. In every aspect of our universe, this quiet but relentless force is always present, subtly directing the flow of energy and matter. As we delve deeper into the theory, it's crucial to go back in time to the era when the concept first emerged. The history of entropy is intertwined with the minds of some of the most brilliant scientists in history. Our narrative begins with Sadi Carnot, a French physicist often referred to as the father of thermodynamics. In the early 19th century, Carnot was fascinated by the efficiency of steam engines, the driving force behind the Industrial Revolution. His research laid the foundation for the laws of thermodynamics, which were later incorporated into the concept of entropy. Carnot's visionary work described how heat engines work and focused on how energy is transferred and transformed. His theories have played a crucial role in understanding the dynamics of energy flow within systems. The next key figure in our story is Rudolf Clausius, a German physicist. Clausius was the one who introduced the term entropy in the mid-19th century. He built on Carnot's ideas by delving into the nature of heat and energy transfer. Clausius's work led to a more formal definition of entropy. He suggested that heat cannot spontaneously transfer from a colder body to a hotter one, the principle underlying the second law of thermodynamics. His mathematical formulation of this concept allowed it to be quantified, bringing clarity to its elusive nature. Another giant in this field was Ludwig Boltzmann, an Austrian physicist. Boltzmann's contributions in the late 19th century brought a statistical approach to thermodynamics. He linked the microscopic behavior of atoms and molecules to macroscopic properties of matter, such as temperature and entropy. Boltzmann's work was groundbreaking. He showed that entropy can be understood as a measure of disorder at the molecular level. His famous formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microstates, gave a profound insight into the nature of this phenomenon. The legacy of these pioneering scientists is immense. Their collective work laid the foundation for modern thermodynamics and statistical mechanics, fields that continue to evolve and shape our understanding of the universe. Turning our gaze to the natural world, we find that entropy is at work in every ecosystem, shaping the environment and the life within it. Nature, in its infinite complexity, is a vivid canvas of disorder in action. Consider a fallen tree in the forest. Over time, it undergoes a remarkable transformation. Microorganisms, insects, and fungi break it down, returning nutrients to the soil. This process of decay and renewal is a manifestation of our principle, reflecting the cycle of life and death in nature. Rivers are also agents of entropy. They constantly change the landscape, cutting through rock and soil, and redistributing sediments from the mountains to the sea. This relentless movement and transformation of matter is a classic example of the role of this principle in geophysical processes. Weather is another area in which chaos plays a crucial role. Cloud formation, rainfall, snowmelt. These are all processes driven by the distribution and redistribution of energy in the atmosphere on a global scale. In the oceans, entropy is manifested in the life cycles of marine ecosystems. Coral reefs, for example, thrive on the delicate balance of nutrient cycles, temperature, and ocean currents governed by the principles of energy flow. Photosynthesis, the process by which plants convert sunlight into energy, is another interesting example. Here, the entropy principle plays a role in converting solar energy into chemical energy, a process fundamental to life on Earth. From the tiniest interactions of microscopic organisms to the grandeur of ecological systems, This fundamental force is the invisible conductor of the natural world. It is the underlying principle that nurtures the beauty and dynamism of our planet. Life on Earth, in all its diverse forms, is deeply intertwined with the principles of energy flow and transformation. This complex relationship between life and energy reveals a universe in which chaos and order coexist in a delicate balance. Consider the simple process of seed germination. This process is a microcosm of life's ability to use and organize energy. As the seed grows, it absorbs energy from the environment, converting it into structured, organized forms. However, there's a price to pay for this organization, an increase in the overall disorderliness of the system. In the human body, entropy is our constant companion. Our cells are energy conversion power plants, constantly converting nutrients into energy. This metabolic activity is vital to our existence, but it also leads to increased disorder as energy is released in the form of heat and waste products. Ecosystems are also valid examples. For example, in a rainforest, the flow of energy from the sun to plants and then through the food chain demonstrates the role of entropy in ecological processes. Each transfer of energy from one organism to another involves energy dissipation, contributing to the overall disorder of the ecosystem. Looking at the bigger picture, the evolution of life on Earth can be seen as a journey through entropy, from the first single-celled organisms to the complex network of life we see today. Evolution has been a process of increasing complexity, driven by the fundamental laws of energy and matter. In the grand narrative of life, entropy is not just a concept of decay or disorder. It's the driving force behind growth, complexity, and a constant cycle of transformation. Life in all its forms thrives in the delicate balance between order and chaos, a testament to the profound interplay of energy and matter. In the cosmic arena, the principles governing entropy show a universe in constant motion, a stage in which stars are born, live, and die in a great cycle of energy transformation. Star formation is a process of remarkable energy dynamics. Inside nebula, clouds of gas and dust collapse under gravity, heating up and eventually triggering nuclear fusion. It's a transition from potential energy to kinetic energy, a cosmic example of energy distribution on an enormous scale. The life cycle of stars can be seen as a narrative of energy transformation. In their final moments, massive stars explode as supernovae, dispersing their elements across the cosmos. This dispersion is a powerful demonstration of the universe's tendency to increase the dispersion of energy and matter. Black holes, in turn, represent one of the most intriguing aspects of cosmic entropy. These mysterious objects, which have such a strong gravitational pull that even light cannot escape them, play a significant role in the energy dynamics of the universe. The black hole event horizon marks the point of no return, where matter and energy are irreversibly absorbed, contributing to the overall disorder of the cosmos. By the way, our channel has already published a detailed video about the connection between black holes, Hawking radiation that depletes them, and entropy. We recommend you watch it. The expansion of the universe is itself a confirmation of these principles. Galaxies are diverging, energy is becoming more evenly distributed over vast space, and the fabric of the cosmos is stretching, all of which indicate that the universe is evolving toward a state of higher dispersion. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a glimpse into the early universe. As we know, this radiation is a remnant of a time when the universe was hot, dense, and in a lower entropy state. Paradoxically, as the universe expanded and cooled, its randomness increased. And this is what led to the inevitable formation of the complex structures we see today. One of the most profound consequences of these cosmic processes is the concept of the heat death of the universe. In this scenario, the universe reaches a state of maximum entropy, where all energy is distributed so uniformly that further energy transformations become impossible. This is a future in which the universe is cold, dark, and devoid of the energetic dynamics that drive cosmic evolution. In this vast cosmic action, the flow and transformation of energy shapes not only the stars and galaxies, but also the very destiny of the universe. It is a continuous process of creation, transformation, and ultimately, disintegration. In the modern world, the concept of entropy has transcended its scientific origins, finding applications in a variety of fields, but subject to common misconceptions. Currently, entropy plays a crucial role in the development of advanced technologies. In the field of renewable energy, a thorough understanding of this concept is essential to improve the efficiency of solar panels, wind turbines, and energy storage systems. This knowledge greatly helps in optimizing the conversion of natural energy sources into usable energy. In the field of information theory, entropy has acquired a new meaning. It represents a measure of uncertainty or randomness in a system. This concept is crucial in data encryption and compression, where controlling and predicting information patterns is essential. Despite its scientific importance, entropy is often misinterpreted. A common misconception is to equate entropy solely with disorder or chaos. Meanwhile, while the definition that entropy leads to an increase in disorder is correct, it is worth clarifying that we're talking about the distribution of energy and the probability of certain states. Another misconception is the notion that entropy can be reversed or overcome. In popular culture, we see images of time reversal or spontaneous assembly of objects. However, according to the second law of thermodynamics, in a closed system, entropy can only increase or remain constant. Modern physics research is considering its impact on quantum mechanics, the behavior of black holes, and the ultimate fate of the universe. Beyond theoretical physics, entropy has practical applications in environmental science, engineering, and urban planning. It helps to model climate change, design sustainable systems, and understand urban development patterns. The future will undoubtedly bring new challenges and opportunities, and our understanding of this phenomenon will be critical in addressing them. Whether it is advancing technology, exploring space, or managing our planet and conserving its resources, entropy remains a fundamental concept that will continue to define our journey into the unknown. Surely you've heard by now that black holes can be so massive that they can outshine entire galaxies? But some of them are quite mobile, so much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints. Frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the ball cluster closest to Earth. What he discovered was nothing short of groundbreaking. a black hole with a mass about 800 times the mass of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But black holes of intermediate mass turned out to be a missing link, mysterious relatives about which everyone has heard but no one has met. An equally interesting question is how these black holes of intermediate mass form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,855 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light-years away from Earth. But what does that proximity mean in the context of black holes? And why is this proximity important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the ejection of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. The main task of Gaia is to map the Milky Way in unprecedented detail, and it was thanks to this painstaking work that Gaia BH1 was discovered. As the closest known black hole to Earth, Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments will be able to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, Black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue? And how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole. Located 5,000 light-years away from Earth, this black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 miles per second. The key to this revolutionary discovery lies in a phenomena predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star. This creates a brief brightening phenomena, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. And this is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling. Its speed is about 28 miles per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star, sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower, and if it's too small, it catches up due to the abundance of gas and dust in the galaxy. So some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young, gas-rich galaxies serve as the birthplace of various black hole phenomena, whether they're luminous black holes or intermediate mass, wandering black holes hurtling through space, or the nearest black holes to Earth. Their origins can often be traced back to these bright young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now, let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory in 2015, opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that reveal a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond or linear pond, the throw of a stone creates an isolated ripple. In a stormy sea or nonlinear, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes in dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merged to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal. You've probably heard of dark matter, the elusive substance that makes up about 1/4 of the universe. That ghostly puppeteer is pulling the strings of the galaxy but never showing itself. But what if dark matter is just the tip of the cosmic iceberg? Imagine a universe where the scales of gravity tip in mysterious ways, where stars and binary systems, two stars orbiting a common center, defy the very laws established by Newton and Einstein. What if their equations are not the final word? Recent research suggests anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current understanding of gravity can fully explain. So, are we on the cusp of a paradigm shift? Is our view of the cosmos not as stable as we thought? In cosmic ballet, stars are the prima donnas that catch our eye. But have you ever wondered how these celestial luminaries come into being? It all starts in the dark, cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, pulling the particles closer and closer until they no longer resist gravity. They merge, triggering a nuclear fusion reaction that produces a star. However, the life of a star does not last forever. There comes a point when the nuclear fuel runs out, and the star faces its inevitable demise. For massive stars, this end is nothing short of spectacular. A supernova explosion that eclipses entire galaxies, if only for a short time. These supernovae are not just cosmic fireworks. They are the forges of the universe. It's in the crucible of these explosions that elements heavier than iron are created. So the gold in your jewelry, the calcium in your bones, it's all stardust. The remnants of a supernova explosion. But here's where the plot gets twisted. In a universe dominated by dark matter, these stars and their explosive deaths are part of a larger scene. Dark matter, with its gravitational pull, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, leading to a higher number of supernovae. In these galaxies, stars form and die at an accelerated rate, creating a dynamic and ever-changing landscape. Recent studies have even quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and the rate of star formation. But what if this correlation is not as simple as it seems? Enter MOND, Modified Newtonian Dynamics. This theory suggests that gravity behaves differently at very small accelerations. If MOND is correct, the high rate of star formation in dark matter-rich galaxies may have an alternative explanation. Double star systems, those cosmic pairs we discussed earlier, can serve as an ideal test laboratory for these theories. Their orbital dynamics can show whether Newtonian gravity persists or whether MOND offers a better explanation. As scientists delve deeper into the data, especially the treasure trove provided by the Gaia mission, we're getting closer to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often portrayed as a silent, mysterious entity that shapes galaxies but remains elusive. One of the most compelling theories attempting to solve this mystery is the cold dark matter model, or CDM. In the CDM model, dark matter is cold, which means that its particles move much slower than the speed of light. This slowness allows them to clump together to form the gravitational scaffolding on which galaxies are built. CDM-based computer modeling has been extremely successful in reconstructing the large-scale structure of the universe. It shows a cosmic network of galaxies connected by dark matter filaments that's very similar to what we observe. But, like any good story, there are unexpected plot twists. While CDM does an excellent job of explaining the grand architecture of the universe, it falters when we get closer to individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should drop sharply as we move away from the center. But observations tell a different story. The rotation curves remain surprisingly flat. suggesting that something else is involved here. Perhaps another kind of dark matter, or even a modification of gravity. And then there are dwarf galaxies, smaller satellites of larger galaxies like our Milky Way. The CDM model predicts many of these dwarf galaxies, but we just don't see as many as expected. These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where MOND enters the scene again, offering a different set of equations that better explain these galactic features. It's like two different scripts of the same movie, each with its interpretation of the main character, dark matter. At check weighing, the scientific community is divided. Is the CDM the final theory that unifies our understanding of the universe, or is it just a stepping stone toward a more complete model? For centuries, Sir Isaac Newton's equations have been the foundation of our understanding of gravity. They've been tested, retested, and retested, and have stood the test of time. But what if there is more to the story? Introducing MOND, or Modified Newtonian Dynamics, a theory that dares to modify Newton's sacred equations. It suggests that gravity behaves differently at extremely low accelerations, such as at the outskirts of galaxies. The goal of MOND, conceived by physicist Mordecai Milgrom in the early 1980s, is to resolve some of the inconsistencies that have arisen in our observations of galaxies, especially those puzzling rotation curves we discussed earlier. You see, MOND fits the observed flat rotation curves of galaxies perfectly, without resorting to dark matter. It's as if MOND is saying, wait, maybe you don't need to invent a mysterious form of matter. Maybe you just need to adjust your equations. And it's not just about rotation curves. MOND has also managed to explain the dynamics of some galaxy clusters, and even the large-scale structure of the universe, without relying on the mysterious dark matter. But of course, no theory is without problems. While MOND succeeds in some areas, it faces difficulties in others, such as explaining the cosmic microwave background afterglow of the Big Bang. The cosmic microwave background, or CMB, is a snapshot of the universe just 380,000 years after the Big Bang. The CDM model, with its dark matter component, explains the features of the relic radiation well. MOND, however, has difficulties here. And let's not forget our celestial pairs, double star systems. Recent studies, some of which we've already discussed, have shown contradictory results when applying MOND to double stars. So what does that give us? Well, at the very least, a state of exciting uncertainty. As new data comes in, especially from the Gaia mission, MOND continues to be hotly debated. Is MOND the missing piece of the puzzle that will finally explain the anomalies we observe? Or is it a useful but ultimately flawed stepping stone towards a more complete theory? In a universe full of questions, sometimes the answers lie closer to home. Just 1.5 million kilometers from Earth orbits Gaia, a spacecraft that may hold the keys to some of the universe's most puzzling mysteries. Launched by the European Space Agency in 2013, Gaia is no ordinary telescope. It's a space cartographer mapping the positions, distances, and motions of more than 1 billion stars with unprecedented accuracy. Imagine having the coordinates of 1 billion stars at your fingertips. It's like Google Maps for the Milky Way, but with a staggering level of detail. One of Gaia's key techniques is parallax, an ancient method with a modern interpretation. By observing a star from 2 different points in its orbit, Gaia can triangulate the distance to the star with incredible accuracy. But Gaia is more than just a space explorer. It's a theory tester. Remember, Those controversial theories about gravity and dark matter? Gaia data can be used to put those theories under the microscope. Take, for example, double star systems. These systems are crucial for testing theories like MOND. Gaia's precise measurements of the positions and velocities of these stars can help us understand which theory is correct. And it's not just stars. Gaia also observes asteroids, planets, and even distant galaxies. Its data have been used to refine the Hubble constant, a key parameter that helps us understand the expansion rate of the universe. Measuring the Hubble constant with Gaia has added a new twist to the ongoing cosmic controversy. Different methods yielded slightly different values, and Gaia's data became an important piece of this cosmic puzzle. But the Gaia mission is not without its challenges. While the spacecraft provides a wealth of data, interpreting that data is a different story. The same Gaia data have been used to both support and refute theories such as CDM and MOND, leading to heated debates in the scientific community. It's like a high-resolution photograph where everyone sees something different. Is it a speck on the lens or a revolutionary discovery? Interpretation depends on sophisticated statistical methods and, of course, on our basic assumptions about the universe. There is nothing more fascinating than double stars. Two stars locked in a gravitational embrace, orbiting each other in a delicate balance of attraction and repulsion. As we mentioned earlier, these dual systems are not just celestial spectacles, they are cosmic laboratories. Here, in the intricate ballet of their orbits, we can test our deepest theories about the nature of gravity itself. Double stars have been a cornerstone of astronomical research for centuries. They've helped us measure the mass of stars, understand stellar evolution, and even confirm Einstein's general theory of relativity. But in the context of our ongoing debate between cold, dark matter and modified Newtonian dynamics, double stars play an even more important role. Their orbital dynamics can reveal whether Newtonian gravity persists or whether MOND offers a better explanation. Recent studies have delved deeper into this question. Some studies, using data from the Gaia mission, have shown that double star systems behave as predicted by Newtonian gravity, casting doubt on the applicability of MOND. However, other studies tell a different story. They suggest that MOND is better suited for some double systems, especially those with large distances between them and weak gravitational attraction. Could it be that both theories are partially correct? Or are we missing a key piece of the puzzle? The scientific community is divided, and for good reason. The stakes are high. The behavior of double stars could either confirm our current theories or send us back to the drawing board in our quest to understand the universe. So, how do we weigh evidence? Meet Bayesian statistics, a mathematical framework that might just tip the scales. Named after Thomas Bayes, an 18th century statistician and theologian, Bayesian statistics offers a way to update our beliefs in light of new data. It's like a mathematical expression of the scientific method itself. Here's how it works. You start with a prior belief, or prior, which is your initial hypothesis. As new data becomes available, you update it before forming a posterior hypothesis, a revised hypothesis that better fits the actual data. In the context of our cosmic debate, be it cold, dark matter, MOND, or something completely different, Bayesian statistics provides a rigorous way to assess which theory is more likely, given the observed data. For example, when analyzing double star systems, Bayesian methods can help quantify the probability that MOND or Newtonian gravity is the correct theory. It's not just about curve fitting, it's about estimating the weight of evidence. And it doesn't just apply to double stars. Bayesian statistics have been applied to a wide range of cosmic phenomena, from the distribution of dark matter in galaxy clusters to the rate of expansion of the universe. Nevertheless, Bayesian methods are not without critics. One of the most controversial points is the choice of a prior. How to choose the initial hypothesis in a way that does not distort the result. The choice of a prior can be controversial because it can affect the results. If your prior leans strongly towards one theory, a posterior may confirm that theory even if the other is equally true. As we grapple with these questions, Bayesian statistics remain a powerful tool in our analytical arsenal. It offers a way to make sense of complex spatial data, sift through the noise, and find the signal. The universe seems to refuse to reveal its secrets readily. Even as we gather more data, the debate about the true nature of gravity is intensifying. Hyun Che, an astronomer who recently hit the headlines, said, quote, "I was feeling like I was dreaming. It seemed so unreal. This is because my results did not match any previous results." Che's work stirred the pot by suggesting that when the gravitational acceleration of stars in certain double systems falls below a certain threshold, they're more consistent with Mond models than with the standard gravity model. But here's the rub. Che's findings contradict several previous studies. He mentions, quote, "One group has been claiming an anomaly for some time, but the anomaly seemed not to match well the predictions of existing modified gravity theories." This discrepancy in results is not just a glitch. It's a fundamental challenge to our understanding of the cosmos. It raises questions about the reliability of our models and the data we use to test them. So what does that give us? Well, at least a state of productive confusion. As Che concludes, quote, "Because the standard cosmology is based on general relativity, cosmology needs a major revision now." The debate is far from over. As we collect more data and refine our theories, the search for the ultimate truth about gravity and the universe continues. And in this quest, every anomaly, every contradictory result adds a new level of complexity and wonder. Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong, each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field, all these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, it's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason: it has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the Sun, the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the Sun is just one node, a lone star among countless others. Close to the Sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our Sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our Sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the Sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the Sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the Sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the Sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the Sun. Although the Sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness, and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our Sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the Sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of a galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our Sun is now. But even stars like our Sun must face change. In about 5 billion years, the Sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our Sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy. past our local group of galaxies and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet, it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder: what other mysteries does the universe hold that we have yet to unravel?